Bergstra, who recently completed his PhD at the University of Montreal, and he's now doing a postdoc at Harvard. Whereas John was telling us what the performance optimization space was and why it mattered to explore it, James is going to be telling us about how to explore it more efficiently, more smartly, using machine learning.
Thank you for the introduction. My talk is titled Machine Learning for Predictive Auto-Tuning with Boosted Regression Trees. And I just want to thank, before I get started, I want to thank certainly Nicolas and David Cox for helping out with this work. And also I want to thank Dwayne for giving a very good introduction to empirical auto-tuning. So I'm looking forward to drawing some connections with the content of the first talk. Usually I'm not like a high-performance computing guy. Usually, I'm a user, and as a user, I love it when a function just looks like the math that it's supposed to implement. And so, as a user, I've got certain desires. Should I adjust this? All right, so I'm looking for libraries with normal mathematical interfaces. Platform independence is awesome because I just want to write my code once and run it everywhere. And I wanted to run it perfectly fast on all the inputs that would make sense for the math. That's what users expect of a library. And, that's hard, right? So this talk's going to be about some tools to make that a little bit easier. So as we saw in the first talk, and in the second talk too, to a significant extent, platforms are very different. So different sized inputs call for different kinds of implementations. Different platforms have different hardware, different numbers of cores, different amounts of RAM. Pretty much they're in different computers. So, to provide an implementation that's fast across the board is impossible. And that point was made very well in the first talk of the session. Programmers that are doing libraries have to deal with all kinds of sort of medium level, I would say, maybe not high level, and low-level concerns. So like how do you actually design a blocking strategy to make your algorithm parallel? How do you choose where to put the memory at various times so that parallel execution strategy makes sense? And sometimes you have to make trade-offs between synchronization, which is expensive, and recomputation, which can actually be really cheap. And then at the low level, like where you actually start generating instructions, there's a host of optimizations that shift pressure between whether you want to use more registers, more instructions, different amounts of shared memory obviously have impacts on the occupancy, and so on. So we've seen before in the talks why all these concerns interact in really complicated ways. And different platforms provide different performance effects, blah, blah, blah. It's really hard. So there are basically two approaches, and if this is oversimplifying, I'd really love for someone to come up and talk to me afterward. But in reviewing the literature, it seemed like there were two approaches that are emerging to how to deal with the complexity of all these interacting concerns. So the first one's empirical auto-tuning, which we saw in the first talk, and the second one's model-driven tuning, which we haven't seen yet so much. I'll just walk through quickly what those two approaches are, and then I'll talk about how I suggest that maybe it's better to look at things a little bit differently. Empirical auto-tuning starts with instrumenting your implementation. So instead of just writing one C code, we would write a template, like we saw in the first talk, where there's a number of parameters that actually control a code generation process. And so you can write a small amount of code, but then it actually corresponds to quite a large family of potential implementations, like a large family of kernels and a large family of column strategies and so on. And in empirical auto-tuning, if you want to know what's the fastest way to sort 1,000 numbers, or what's the fastest way to multiply two matrices together of a particular size, it's pretty straightforward. You just try them all, and you figure out which one's the fastest. It's a great approach. You just save the one that was the fastest of all the implementations that you tried, and then you're pretty much guaranteed that when the user comes along with a matrix of just the right size, you're going to give him the fastest implementation for that input. one con is that it is difficult to find, it is a slow process. Obviously here in step 2, all right, they're not numbered, misnumbered. The second point is that you start off by actually evaluating the computation you want to perform about like 1,000 times. So at runtime, that's not really making a lot of sense. This has to be done ahead of time. So systems like Atlas or FFTW start off with the installation process that takes hours, where they actually go through and measure how long these things take. And at the end, what you have is a list of like, if the input's exactly this size, then I should use this implementation. If the input's exactly that size, I should use this implementation. And this database is pretty dense, actually. You have to say exactly what to do for every single input size in the problem. And the example this morning about sorting is actually a good one for when this works, because there's only one dimension along which the input changes. It can be shorter, it can be longer, and then you can say for various ranges what to do. But in a case like matrix multiplication, there's 3 parameters about the sizes. And I'm going to talk about later on an example of filter bank correlation, where there's 5 or 6. And in more complicated, denser kernels that people use to really take advantage of the locality of data, there starts to be more and more parameters that are controlling the problem you're trying to solve. So this approach doesn't really, answer everybody's. This is not the tool that the library providers have been waiting for. And certainly, when you change to a different platform and you're no longer running on the GTX 480 that you ran all your experiments with, bets are off. You have to do your tuning again. This is a quick graphic that corresponds to what were several graphics in the first talk, illustrating that for a particular kernel, which I'm not going to explain what it is, there was a reference implementation which was pretty fast. That's the middle blue bar. And by auto-tuning for various input sizes on the left, you can get, for this particular kernel, an average improvement of about 20%. And just as sort of a demonstration of how brittle this is, on the rightmost bar where it says mismatch, what we've done is like empirically auto-tuned for, I'll give it away, it's filter bank correlation. So we're correlating small filters with big images. And if we auto-tune for the wrong size of filters and the wrong size of image, and then use that implementation for the one that the user actually wants to be evaluated, the performance is terrible. So this is sort of a silly thing to do. This is not how auto-tuning is meant to be used, but certainly there is evidence of these performance bits that some of you may know about. The other approach that's different from empirical auto-tuning is model-driven tuning. So in model-driven tuning, you're also going to start by instrumenting your implementation. So you're going to say, you're going to make a code generator. And instead of measuring all the time, you're going to make a function that tells you how long it's probably going to take. So you don't have to measure. You make a simulator. And then, sort of in the spirit of this just-in-time search, when a user says that they want to multiply a matrix that's really tall by one that's really fat, then you plug that into the simulator and you figure out how long each of the implementations is going to take. And then you actually run the one that's the fastest. And in theory, that can work really well. It's a perfect approach. It's just like auto-tuning, but it's fast. The con is that it requires a simulator who's going to write that. It has to be really accurate. It has to be up to date for all the different hardware platforms. It might include a whole lot of details that are actually irrelevant to your computation you're going to do. And so, building simulators for all the different platforms you might want to use is just like not really an option that's going to take for most applications. So what we're providing is, or what we're suggesting to use is what's called predictive auto-tuning. We're calling it that. And it's the best of both worlds. That's the pitch. You start by instrumenting your implementation, as usual, and then you instrument your problem. So that's new. This means, whereas your original implementation might have had a number of like, I'm going to use blocks of size 8 by 8 by 16 or something, and there's these numbers that say how to actually generate a code. The second option, I'll give you some examples in a second, but the second point here is that you're going to instrument the problem so that if you're going to do matrix multiplication or something, the 3 numbers that are critical to describing the math of matrix multiplication are the dimensions of the arguments. And so those will be like parameters that describe the problem to be solved. And third, likewise, you can use techniques to characterize the platform which you're going to execute. So if bandwidth between global shared memory and such, that's a number you can plug in. Or if you've got a register file that's this big, then that's a characterization you can use to characterize your platform, regardless of what the identity string is. That's a sort of an abstract characterization of what's possible. And then, in the spirit of empirical auto-tuning, we're going to sample all three of these quantities, not just the first one. So for various problems, various implementations, various platforms, we're going to measure how long does it take to actually compute the mathematical result. Then, we're going to use machine learning. We're going to take the top three things as a data set. These are predictive variables. And then the fourth thing is predicted variable. And then rather than write the simulator by hand, we're going to, here we're going to use regression trees. So we're going to fit a predictive model that we can then substitute into the model that we're not tuning. So in images, I'm just going to reiterate what we're doing here. The problem configuration, that's like how big the matrix is. The second thing is implementation, that's like how big the blocks are. And the hardware on the right, micro benchmarks or device inspection that provides this characterization of the ground root. Then empirical auto, you run the function and measure how long it takes, and then you make a fit function that predicts the timing from the features. So to validate this idea, we did go up to a problem that has a certain number of, or more than one dimension. So this was the motivating example that we began this work on computer vision and image processing, where filter bank correlation and convolution are very important bottlenecks. So they aren't really addressed by the CUDA, loss, or any of the other libraries that NVIDIA provides. So practitioners have to kind of hack their own things together. And the math here is that for every patch in the input, we're going to do an inner product. Oh, I wish I had this. But here it is. Okay. So for every patch in the input, we're going to do an inner product with one of these filters, and then that scalar will be written to one of these output buffers. So there's a certain number of filters. They all get involved with the image to produce a certain number of slices in this output buffer. It turns out that the arithmetic intensity of this operation is pretty high, so GPUs are really good at it. And there's a number of opportunities for parallelism. And, every one of these scalars can be computed independently on every one of the slices. And even the inner product can be separated in case the patches are relatively big compared with the overall image down here. But you can see that for different sizes of patch relative to the image, for different sizes of image, for different numbers of channels, like red, blue, and green here, for different numbers of filters, for different, the strategy for parallelization, the strategy for computing these things changes quite a lot. So it's important to be able to navigate a large space of possible implementations. The implementation that we used was based on the filter bank correlation code of Pinto and Cox 2011, which is in the paper. I'm actually not going to show you the file. It's like this HTML templating engine generating crazy code, but it's sort of similar to the preprocessor, but really, like, it can do loops and stuff. So there's a whole bunch of parameters that go into the code generator that are like how big the blocks are, how many rows to compute at a time, whether to do register scaling, whether to use the old style multiplication or the new, and so on. So these are all the different parameters that go into implementation. And so the feature space consists of these numbers here, like the number of filters, the height, width, rows, and columns. The block height, whether to use texture, fetches, and so on, and platform features. We didn't actually get into platform features. Sorry to roll that up. Got disappointed. That's future work. We'd like to pursue that later. For the timing model, it's important to get the timing model right. So here's one of the subtleties of our approach. So it's important to, well, when you fit a machine learning model, what you do is minimize an average cost. Like if you predicted it'll take 3 seconds and then the actual time was 2 seconds, there's a difference here that's going to be squared to produce a measure like whether that prediction is accurate or not. And it turns out that if you just predict a number of seconds, it doesn't really reflect what you want. So we actually have in our hands a good reference implementation. And so we wanted to optimize the average speed up that you would get over top of the reference implementation that we started with. So we chose this scaling function here. So that, of course, doesn't quite work in the case that there's some valid configurations where you're asking too many registers or something like that. And then so we just made up some default like amount of time to attribute to configurations that didn't work at all. It was important to make this time longer than the reference actually took. So we'll never choose that as being better than the reference. So the regression trees that we learned here have the form of being choices about whether, here for one feature like the number of image rows, if it's too big, if this is a big image, then if our kernel generator is actually allowing lots of registers, then probably the speed up is going to be about 2.5. And if not, probably speed up 1.5 for smaller images if the block height was chosen to be less than a big number. But then you get a negative, because that's actually like slower than the reference. And then this was actually enormously faster than the reference. So you can build up these regression trees, and regression trees are nice because they support all the different kinds of variables. Some of the variables that we're trying to search through are discrete values, some of them are continuous, some of them are just binary choices. And also there's a fast, simple learning algorithm. We did not invent regression trees, these are old models. The trouble is that they're not that accurate. So instead what we did was we boosted the regression trees. So we fit a bunch of them and then added them together. And there's an algorithm for doing that. So we make a predictive model that is pretty accurate. At call time, that's when the magic happens. So quickly, we need to identify for a new input that we have never seen before, what is going to be the best implementation to use. We did what's shown here in green is like the implementation parameter space. So this is supposed to be like a three-dimensional kind of decision tree surface thing. And the question is, where in this space is the fastest implementation according to our predictive model. So we had this thing, we were just kind of jumping around. This is a kind of a silly algorithm, but it did the job. Future work is to make a better one. So we search through the space. Every time our point gets worse, we backtrack, and eventually, hopefully, we get to the top. Return an implementation that is really promising, and then we just try it. It turned out that most of our experiments, 50 or 75 steps of this jumping around, was just fine. And so what you see here is results on a GTX 580, where for different numbers of training configurations, so depending on how many points we use to fit the model in the first place, we get more accuracy. So if we use more points for training, then we get a more accurate model of empirical auto-tuning, which is the gold standard we're aiming for with this predictive strategy. And so if we just zoom in on the right-hand point here, then you see that if we make a scatter plot of the predictive performance versus the empirical auto-tuning performance, it lines up along a nice straight line. So our predictive model is actually able to identify the implementation that gives the full speed up on points that is never seen before. And that's what allows us to do kind of like a just-in-time implementation selection. And the difference is that like this, it takes a fraction of a second to do that kind of lousy Python implementation. If I do say so. On different data, on different cards, the 295, the Tesla 1060, the GTX 480, and the Tesla 270. This is probably the best fit as far as that goes. But you can see that in all the cases, it lines up roughly along the diagram. So our model is good enough to be used. In case you're wondering about what happened to that little zeta, those invalid configurations, part of the training process was like giving a score to it. There's crappy models that don't work. And it turns out that that score doesn't matter very much. So this red line here is a pretty bad choice, but like all these other choices are pretty reasonable and perform about the same. So to summarize, scientists rely on mathematical abstraction boundaries, and it's important as library providers that we strive to provide those. It is a reality that the new hardware that we want to program demands a multiplicity of implementations, and we just have to think of strategies for navigating in that space. And we put forward predictive auto-tuning as a standard in the sense that there's nothing about the decision trees or the platform features or the problem feature. Well, I guess problem features are coupled to the filter by correlation example, but the idea of building a predictive model and optimizing it when you need, that would work for the searching example, and that would work for quite a wide variety of different algorithm families and mathematical functions that you need to deal with. Future work is generalizing across the hardware platforms, like I mentioned, and writing the forest up, like really just so that model that's a sum of decision trees is called a decision or regression forest, sorry. And I want to have a better optimization that's faster than that. So thank you for your attention and your questions.
Questions from the audience?
So you had mentioned that the way you sort of actually write the software is kind of also difficult because you have to express it in its native language like CUDA, but also inside of snippets inside of something else that is more of a meta composer that assembles the snippets and stuff like that. So is it difficult to reason about sort of two languages at the same time that share discrete type systems? Or, I mean,
yeah, that's fair. That's fair. I think it is a harder. I mean, it is easier just to write a kernel that does one thing for sure. And the templating approach, I think, that you were talking about earlier, also runs into that.
It's also just
code generation
I was
stuff.
wondering if you had any ideas for like what would be the best thing to do if you started over in terms of language design. Like, I totally agree with template stuff is somewhat verbose and awkward as well for doing the same purpose. So,
Yeah, it would be great if I think Lisp is great for this actually. Maybe not very popular at this conference, but Lisp has this beautiful structure that you can manipulate the abstract syntax tree and be playing not only with different values for like block sizes to take one sort of token in the language that you write, but then you can also apply transforms to the level of the logic itself. Where you replace ifs with switches, you replace loops with unrolled things, and so on. So either it's compiler support or else failing that different code representation entirely.
Any other questions? So I have one. I was wondering if you thought whether this technique can apply to situations where the performance depends on the input data in more opaque ways rather than just on dimensions.
Right, so anything that you can compute as like a statistic quickly would fit naturally into this approach. So the trade-off then is like, if you need a piece of information to make a decision, is it better to compute it and then make a code generation decision? Or is it quicker to just, take a Hail Mary and not compute it first? So but that's a kind of trade-off that this approach, puts in a place where you can start to think about whether it's better to do one or the other. And then whether it does actually or not, it makes sense to do that in your application.
Great. Let's thank the speaker again. And our next speaker